All right, we're recording now. Sorry for people watching this later on. You missed the first 5 minutes, no, the first 9 minutes. I did a little recap, and then we're doing just a simple example here, and we're going to do a couple more examples. So hopefully you can catch on without a problem. I am just simplifying fractions here, right? 6 over 9 divided by 8 over 9. The over 9s will cancel, and I get 6 over 8. In other words, 3/4. That's the answer to this series. That's what it adds up to. All right? This is how we do it. I got a couple that I wanted you all to try. To evaluate, or perhaps say that it diverges. 5 over pi to the n, that'll be fun. And another one, sum n equal 1 to infinity. -4 to the n minus 1 over 3 to the n. All right? These are both geometric series, so you can evaluate them using the same methods as I just did up there. All right, I'll give you a moment. See what you think. Any questions from the folks on the Zoom? Sorry, I can't walk around and see how you're doing. I bet you're doing great. I have no way of knowing that, but I hope so. Let's take a couple more minutes and then we'll go over them. All right, let's talk about them. I don't know if you're all done yet, but that's all right. So the first one, 5 over pi to the n. The folks in the room, I saw finish this one off. You should write out a few terms. Really, you only need the first 2 terms to figure this out. The a will be the first term, which is 5 over pi. And then the r is the ratio of the second term divided by the first. So 5 over pi squared divided by 5 over pi. You got to keep it straight with the fractions and all that. This, of course, I find it easier to write when I have fraction divided by another fraction. It's the same as the first one times the reciprocal of the second one. However you want to simplify that. Anyway, you get 1 over pi for the r. I hope that's what you got for the r. Remember, we must check that this is in the appropriate range for convergence. So what is the absolute value of r less than 1? Absolute value of r means, well, this is already positive, so it is 1 over pi. Is that less than 1? It is, because pi is something like 3. 1 over pi is like close to a third, so it is less than 1, all right? This is less than 1. Or you could just say that's a fraction where the denominator is bigger than the numerator, so it's less than 1. So it converges, and what does it converge to? Converges to a over 1 minus r, which in this case is 5 over pi over 1 minus 1 over pi, all right? And that's that. You could, I suppose you could plug that into your calculator if you want to. I don't really care about simplifying. I think probably the best you could do to simplify would be multiply through everything by pi. It's 5 over pi minus 1. That's a little simpler, but I don't care about that. All right, any questions about that? I hope the Zoomers got that one. All right, the next one, same idea. We begin by doing the a and the r, right? So the a is the first term, which is 1/3. That's easy enough. The r is the second divided by the first. That will be negative 4 over 3 squared divided by 1/3. And when I simplify this, if you like to write it as multiplication instead, 3 over 1 there, not 3/2. I think I'm going to get negative 4 over 3, right? Yeah? Yeah. So this is the r. We check, is r in the appropriate range for convergence? Absolute value of r, I need absolute value of r to be less than 1. Here, absolute value of r is 4/3. This is greater than 1. This is not less than 1. So here, absolute value of r is greater than 1, so it diverges, and that's it. All right. This can be a little tricky because if you don't check this, then you would still be able to write down some answer, and it looks like you got an answer, but actually it doesn't converge, and so whatever you thought the answer was going to be is not the correct answer, even though the formula, nothing goes wrong in the formula. You still get something, but that something is a red herring. It's not the answer. Diverges. All right? Don't forget to check if it converges or not. Excellent. That's it for those examples. I just wanted to do one more type of example, and then we'll move on to talk about some other types of series. Geometric series can be used to, we can sort of compute, I will say, kind of in quotes, repeating decimals This is kind of cute, I think. For example, what number is 0.555 repeating? All right. I'm going to write this as 0.5 with a little bar over it. This means no. It's actually 5 over 9 because 1/9 is 0.1 repeating, and this is 5 times that. But I want to talk about how you could, for repeating single digits, how could you decide what this value is? So can I just say it's 5 over 9? That's because 0.9 repeating, sorry, it's because 1/9 is 0.1 repeating. And if you believe that you can multiply that by 5, digit by digit, then what you get is 0.5 repeating, right? But I want to try and compute that without this sort of magical just knowledge ahead of time that 1/9 is 0.1 repeating and then multiplying it by 5. You can actually make sense of this as a geometric series. Check it out. What this means, so 0.55555, etc. This means actually, at some point in your life, you learned this about decimals. What it means is 5/10 plus 5/100 plus 5/1000, right? That's what each digit means. This is the tenths. This is the hundredths, right? Everybody knows that. Hundreds, etc., right? So when I write a decimal number like that, it means I'm adding up certain digits divided by powers of 10, or multiplied by powers of 10 if it's on the other side of the decimal point. All right, in other words, you could write it this way: 5 times 10 to the minus 1 plus 5 times 10 to the minus 2, etc. And this is a series, isn't it? It's an infinite sum, a sum of infinitely many things. That makes it a series. And, in fact, it is a geometric series because the ratio of any one divided by the previous one is always going to be the same. In this case, it's going to be a tenth, that r. So this we can compute. We can compute the answer as a geometric series. And in this particular example, the a is always the first term, so 5 times 10 to the minus 1, and the r is the ratio of the second, 5 times 10 to the minus 2, divided by the first, 5 times 10 to the minus 1. Cancel that business out, I get 10 to the minus 1, right? In other words, 1/10. So the r is 1/10. And then we can use the formula, right? The r here is in the appropriate range for convergence. Absolute value of r is less than 1 in this case, because it's 1/10. That's less than 1. So 0.5 repeating is equal to a over 1 minus r, which is 5/10. That's 5 times 10 to the minus 1, divided by 1 minus 1/10, which is 5/10 over 9/10, which is 5 over 9, which is what I said it was at the beginning. But this is sort of like the real proof of why that is 5 over 9. All right? Pretty great, I think. Any thoughts about that one? I got 2 more interesting examples of this same type. So let's try something a little fancier. How about 0.731 repeating? All right. Here I have 3 digits which are repeating over and over again, right? This means 0.731, 731, 731, etc. All right? Same trick. I want to turn this into a series somehow. Now, it doesn't quite work in the same way. Let me try one attempt. This is not going to work, so don't write this down, but you could try saying just the same way that I did before. It's 7/10 plus 3/100 plus 1,000. Then I go back to 7 over 10,000, and then 3 over the next power, 100,000. I think that's enough zeros, etc. Right? This turns out not to be a great approach because when I write it that way, it's not geometric. When you do the ratios, if I divide one by the previous, like in the first one, if I divide the second one divided by the first one, I get something like 3/7 with a multiple of 10 in there. But if I did the next one, I'd get something like 1/3 with a multiple of 10. It's a different answer every time. So this will not work. Instead, so that's a decent idea, but it turns out not to work because those numerators are different every time. We need the numerators to be the same every time in order for this to be a true geometric sequence. Here's the trick. Combine those terms so that the numerators are always 731. So instead of writing it that way that I did before, I'm going to write it this way. It's 731 divided by 1,000. Because these are the repeating groups, you view them as groups. So the first three groups there is 731 thousandths. And then the next group, 731, is 731 over, can I just say this is 10 to the 3 down here? The next one will be 731 over 10 to the 6. And the next one will be 731 over 10 to the 9, etc. All right. This is the trick you use when you are repeating more than one digit. You group them together and you modify those denominators appropriately. So what I have, I find it easier to write these using negative powers. So what I have is 731 times 10 to the minus 3 plus 731 times 10 to the minus 6, 731 times 10 to the minus 9, etc. And now those ratios, each one divided by the previous one, they will be the same every time. What I wrote before in red up there, they were going to be different every time because you have the 7 on top, then the 3, then the 1. But here we have 731 every time, so it's going to work out great. Let's see if we can do it then. The A this time is going to be the first term, as usual. The R is the quotient of the second divided by the first. Those 731s will cancel, and I get 10 to the minus 6 divided by 10 to the minus 3, which is 10 to the minus 3. All right, this, of course, is 1 over 1,000, which is definitely in the appropriate range for convergence, right? 1 over 1,000 is absolute value less than 1. And so it converges. What does it converge to? It converges to, A over 1 minus R, which is, A is 731 times 10 to the minus 3, which I'll write as 731 over 1,000, divided by 1 minus 1 over 1,000. This is 731 over 1,000 divided by 999 over 1,000. And then those thousands will cancel in the fraction, and we end up with 731 over 999. That's the answer. All right, pretty great. Any comments about that one? So any kind of repeating decimal like that is possible to convert back into a fraction in this way. Of course, if you want to go from the fraction to the repeated decimal, it's much, much easier. You just do the long division. But to go from the repeating decimal back to a fraction, you got to sum the geometric series. All right. One more example, which is actually easier than this one that I just did, but something that I hear kids talking about on the playground sometimes. How about 0.9 repeating? What is that as a fraction? 0.9 repeating. It's like almost 1, right? I don't know if you've ever talked on the playground about 0.9 repeating. What is this? Well, if I write it as a series, it's 9 tenths, so 9 times 10 to the minus 1 plus 9 times 10 to the minus 2, 9 times 10 to the minus 3, etc. Right? And then I can do the same old stuff. The A is the first term, so A is 9 times 10 to the minus 1. The R is the ratio. 9 times 10 to the minus 1 divided by 9 times 10 to the minus 2. We cancel the 9s, and we end up with just 10 to the minus 1, which is 1/10. 1/10 is less than 1, so it converges. Absolute value r less than 1, so it converges to, what does it converge to? A over 1 minus r is, A is 9/10 divided by 1 minus 1/10. This is 9/10 over 9/10, which is 1. How you like that? So the next time you hear the kids on the playground talking about 0.9 repeating, you tell them 0.9 repeating equals 1. In a sense, there is no such thing as 0.9 repeating. I mean, there is such a thing, but it's the same as 1. There's no other number that's like the last number before you get to 1. There's no such thing as that. It's the same as 1. Something like that. I mean, what somebody means when they say 0.9 repeating is really they mean this series, which is getting, at every time you add more stuff, it gets even closer to 1. And so if you actually consider the whole thing, which is if you actually allow this to repeat sort of forever out to infinity, it actually equals 1. It's not a different number that's like really close to 1. It just straight up equals 1. All right? This fact is deeply disturbing to some people. There's a Wikipedia article about this fact. It's called, I think the official name of this article is 0.999 ... equals 1. I think that's the title of the Wikipedia article. And if you look at the discussion page for that article, you can see many, many people come along and try to argue somehow that this is not mathematically true. Those people do not believe in the summation formula for geometric series, apparently. It's a true fact. What's weird about this is, what it means is decimal, this is an uncomfortable fact to some people, decimal representations of numbers, some numbers at least, are not unique. That is, there are certain numbers which you can write in two different ways. For example, 0.9 repeating is the same as 1. Now, if I wanted to be totally technical about this, I would write it that way. 1.0 repeating, right? Those two are two different decimal representations, but they represent the same number. This is not the only case where this happens. Actually, you could do something like 0.49 repeating. Anyone want to say what does that equal? In other words, this is the same as 0.5. Yeah. And if you want to be super technical about it, you could say 0.50 repeating, right? This is another case of two different numbers which have the same decimal representation. Two different decimal representations which indicate the same number. Right? This is the number 1/2, both of them.
Now, if you put 0.5 and then you get 0 repeating, and after that 0 repeating, adding it down, would it be this 51 or 0.5 now?
You can't do after the 0 repeating.
You can't add a decimal after, like another.
No. Because the repeating means this repeats forever. You can't say it repeats forever and then you get one more. There's no such thing as that.
Well, I mean, if
right?
it repeats forever, then theoretically there's always another place for a number.
Yeah, but it's always going to be a 0. That's what repeating forever means. Yeah, there's no sort of like, this is impossible to make sense of as a decimal number. Like, when you write a decimal, each number you write here is meant to represent a power of 10 in some position, right? This is the 10th place. Now, when I put the bar here, that indicates that all subsequent places are 0, right? And then you can't say, and then you get a 1. After the bar means everything is going to be 0 from now on. Yeah, this one can't possibly represent any meaningful decimal location. Strange fact, though, not all numbers can be written in two different ways. For example, 1/3 is 0.3 repeating, and that's the only way to write 1/3 as a decimal. It's a strange, so certain numbers you can write in two different ways, but certain other numbers they do have a unique decimal representation. This is the only decimal representation. Yeah, it's weird. I think from a certain point of view, it's not really weird at all, but I think what makes it seem weird is that we are taught from a young age to think of numbers as decimals. Like, this is how it's sometimes described to, like, kids say, like, what is a real number? A real number is anything you can write as a repeating or non-repeating decimal expansion.
I would also argue that we're taught that numbers are unique, and so when you see the number 1, that the number 1 can only mean 1 or 1/1. And so when you see it like this, 0.9 repeating equals 1 just doesn't necessarily fit.
Right, because you want to think that 0.9 repeating is a different number from 1, because they look different.
It appears that way.
Yeah, they look different in their decimal, but they are not different numbers. I mean, it's kind of like saying the number 3 is the same as 3/1 and is also the same as 6/2. These are three different ways of writing the number 3. They're all equal, even though they look different. Now, no kid is ever taught that looking at a fraction, if the fractions look different, everybody knows if the fractions look different, they still might be the same. The same is true of decimals, though. If the decimals look different, they still might represent the same number.
Okay, I'm still a little confused on how you get there. Would that 0.999 be represented as a limit in terms of how it's explained to equal 1?
Yeah, so 0.9, it is equal to this series, n equals 1 to infinity of 9 times 10 to the minus n, right? Yeah. And that, I mean, I didn't write lim here, but really the true definition of that series is as a limit. It's the limit as n goes to infinity of the sum of the partial sums, right? So it is a limit. Yeah. Strange but true facts about the real numbers. Decimal digits are a helpful way of writing down numbers, but they don't actually uniquely determine the number. Not always. All right. That's all I want to say about that. Tell your friends, 0.9 repeating is equal to 1. It's true. 0.3 repeating is equal to 1/3, and not anything else. All right, another important example of a series. So we've said pretty much all there is to say about geometric series. That is a series in which the ratio from one to the next is always the same, or from one to the previous is always the same. There's another type of important example of a series is called the harmonic series. Unfortunately, these names, the word geometric versus the word harmonic, it's hard to keep them straight because there's nothing really about the geometric series as we've been talking about. There's nothing really geometric about it in the traditional sense of geometry. I mean, there are historical reasons why we call it that, but you just sort of have to remember. Geometric means the same common ratio every time. The harmonic series refers to this specific series, the sum of 1 over n. n equals 1 to infinity. So to write out these terms, it would be 1 plus a half, plus a third, plus a fourth, and so on. This is called the harmonic series. And this one I want to talk about for a few moments, but there is no formula for what this adds up to, and that's because this diverges. In fact, it diverges to infinity, so the limit is infinite in this case. All right? I don't know about you, to me this was a surprising fact when I first heard about this, because these things, you know, every time you add the next one on, the next one that you add is going to be even smaller than what you had before, right? You add a fourth, next will add a fifth, then a sixth. Eventually, when you go down, really far down this list, you're adding on things like 1 over a million, 1 over 10 million, right? It turns out, though, for reasons which we'll see in a moment, the limit of this is still infinity. Actually, adding those millionths or 10 millionths, they actually do add up and make the thing become infinite. They do not sort of add up and converge to some particular value. Very strange, and to me, surprising fact. Let me try and convince you of that. Why does this go to infinity? What you have to do is you have to look at, of course, the partial sums, right? S1 is just the first thing. S2 is the first plus the second, right? S3 is the first three. 1 plus a half plus a third. I didn't mean that. I meant S3 really just has the first three things, right? I meant to put dots like that. You keep on adding things together. If we look only at powers of 2 in the S's, so S, starting with S2, this of course is 1 plus a half. I already wrote that one. S4 is 1 plus a half plus a third plus a fourth. But check it out. If I group those two together, I'm going to make an inequality here. This is greater than, got to get it straight here. This is greater than 1 plus a half plus 1/4 plus 1/4. I just changed the 1/3 to a 1/4. I increase the denominator, so it makes the number smaller from one step to the next when I increase the denominators. And so S4, whatever it is bigger than this number, but that inside the parentheses, those add up to a half, right? So this is the same as 1 plus a half, which I'm going to write as 1 plus 2 halves. Now, this equals 1 plus 1, which is 2, but for the sake of what I'm about to write, it'll look better if I say 2 halves, all right? Okay, that's what S4 is. So S4 is bigger than 2, right? S4 is greater than 1 plus 2 over 2. Okay, what about S8? I said I was just going to look at the powers of 2. S8, all right. I'm going to group them again. This time I group together all the new ones. This time, 1/5 plus 1/6 plus 1/7 plus 1/8, right? And I'm going to do the same trick where I replace denominators with bigger numbers. So this is greater than. I leave the first two the same. In this first grouping of parentheses, I'm going to go to fourths again. And then in the last grouping of parentheses, I'm going to make everything have 8 in the denominator. 1/8, 1/8, 1/8, 1/8. All right? Now, as I did in the previous step, the first group of parentheses, that's a half. And then what about those ones? The group of parentheses with the 8s? Well, there are 4 of them, so this adds up to 4/8, which is, again, a half. All right? So S8, then, is greater than 1 plus 3 halves now, right? Because now there are 3 halves there. Let me just say, similarly, S16 is going to be greater than 1 plus a half plus a half plus a half plus a half, right? When you add in the 16ths, you do the same trick. You make a new block of fractions, 1 over 16, but there will be 8 of them, and so they will again add up to a half, all right? So when I go to S16, I just get another half. That is 1 plus 4 halves, all right? It is a fact, so can I just say each power of 2 makes the sum increase by another 1/2, right? Every time you go to the next power of 2, you get another 1/2. But if the sum increases by a half every time, then that means it's going to go to infinity. If we continue to add together all those terms, every so often it goes up by a half. And so it has to eventually become larger than any individual number. Each power of 2 makes the sum increase by half. In particular, we can say s to the 2, s term 2 to the power n is greater than 1 plus n over 2. This right here, this goes to infinity as n goes to infinity, all right? If I take the nth power of 2, that term is more than 1 plus n halves, and that part is going to go to infinity. All right, this is why the harmonic series goes to infinity. So, in conclusion, the sum n equal 1 to infinity, 1 over n, it actually equals infinity. It does not converge. It diverges. All right. This is called the harmonic series. So you don't need to remember, the formula for the harmonic series. It doesn't have a formula. It diverges. But it's an important example. Come on now. It comes up a lot in different contexts, so it's important to be familiar with this example. All right. This is similar to, actually, the relationship that I'm about to mention is something we're going to talk in quite a bit more detail about later on. But this is similar to the fact that the integral from 1 to infinity of 1 over x is also infinity. That integral is the area under the curve of a 1 over x, is continually shrinking, this area here. But that area, even though it's getting smaller as you go off to infinity, it still diverges. It doesn't actually converge to a particular value. That area is infinite, even though it gets smaller as you go out to the right. All right, this is the harmonic series, and it diverges just in the same way that that integral there diverges. All right. Something, in my opinion, especially weird about the harmonic series, let me just say again, the sum 1 over n equals infinity. Even though the individual terms get very small, individual terms get very small, right? The individual terms are 1 over n. Individually, those, they approach 0 as the n gets very large. Even though the individual terms gets very small, their sum is still infinite. This is weird. Let me just say their sum still diverges. All right? Strange but true fact. It can happen. Even though the individual terms get very small, the sum diverges. What that means is, if you know the individual terms are getting small, it doesn't mean you can conclude that the sum converges or diverges. All right? I'll say it this way. The terms getting small does not guarantee convergence. Right? In this case, the terms get small, but it still diverges. Actually, if you think of this the other way around, there is something that you can say about the relationship between converging and terms getting small. We can say this, though. Here's a theorem about convergence and the smallness of terms. It says, if the series converges, then it is necessary that an, the lim, n goes to infinity, an, must equal 0. All right. If you know the series converges, then the limit of the individual terms must be 0. This is kind of the other way around. For the harmonic series is one in which the limit is 0, but the series does not converge. This is the other way, though. If you already know the series converges, it means that the individual terms, their limit must be 0. I actually want to do a proof of this theorem. It's very simple. I don't like to do long-winded proofs in this class. But this one is really quite easy. We are assuming that the sum an converges. So let's say that the sum an, since it converges, I'll call it x, right? It is a sum. It actually does add up to a particular number. Then here's the trick. Of course, this means that the lim of the partial sums, Sn, equals x, right? The partial sums are that's the definition of what the series is. The series is the limit of the partial sums. So the limit of the partial sums equals x, all right? So check it out. Here's the last trick that you need. I shouldn't say so yet. Also, an, this is a somewhat common trick. An is equal to Sn minus 1. Remember what Sn means? It means the sum of all the terms up to an, and then you stop. Sn minus 1 means you sum all the terms up to an minus 1, and then you stop. If you were to subtract those two, everything would cancel except for the one at the top, which is just an. All right? But anyway, if you believe that, then you can immediately say the lim of n goes to infinity. This is the same as lim n goes to infinity of Sn minus 1. But this, by our limit rules, you can take the limit of each part separately. This is equal to the lim of Sn minus the lim of Sn minus 1. Lim of Sn means what does Sn approach? Well, it is x, right? It still says that up at the top. The limit of the partial sums is x. And what is this one? The limit of Sn minus 1. That means you take the partial sums and you go out to infinity, only you're always, instead of looking at n, you're always looking at the n minus 1. But if they converge to x, even if you're looking at like the second to last one, that also converges to x. This is also x. And so you get 0. And that's what we wanted to show, right? So lim n goes to infinity, an is 0. Because when you break that limit up, you get x both times for the two limits. Alrighty. So the moral of the story here is, if it converges, it is necessary that the individual terms approach 0. But that's not enough to guarantee that it converges, right? Sometimes the individual terms can approach 0 even though it doesn't, the series diverges. All right. This theorem here, this theorem can be used to show that things diverge. So we can use this, I will say sometimes. I underlined it. I meant to put it in parentheses. Sometimes to show divergence of some series. Series in mathematics, the plural of the word series is series. I find this frustrating, so I often say serieses when I serieses. Yeah, I guess it sounds like Gollum. That's the way he talks. Some series, plural. All right, we can use this sometimes to show. So what I said before, this theorem is if it converges, then the limit of the individual terms goes to 0. Another way of saying that the other way around, if the limit of the terms does not equal 0, that means it does not converge. So I'm going to write it in that way. If lim an is not 0, then the series diverges, right? This is logically the same as what I said before. I'm just saying it the other way around, all right? What I said before was if it converges, then the limit must be 0. Saying the other way around, if the limit is not 0, then it does not converge. So if the limit is not 0, then it diverges. All right? This is the, there's a word for this in logic. This is called the contrapositive form of the previous statement. I'm saying the same thing, but in a sort of a backwards way. It's called the contrapositive, yeah. Yeah, if you take we have a class called Discrete Mathematics in which you will learn stuff related to that sort of logical, basic names for various logical constructions and such. Yeah? Yeah, it's good. I mean, it's required for the math major. Most math minors, many math minors take it. I don't know about most, but yeah, okay. It has nothing to do with calculus. So if you want to break from calculus, take discrete math. It's totally different. You will not use your calculator in that class. Anyway, some examples to show various things diverge. For example, how about this? The sum minus 1 to the n. We've already talked about this example, but you can see immediately that this diverges because the individual parts, the individual terms do not approach 0, right? Because minus 1 to the n, if I were to write those terms out, it looks like minus 1, 1, minus 1, 1, etc. This does not go to 0, right? And if the limit of the terms is not 0, then the series definitely diverges. So this is a very easy way to show that minus 1 to the power n diverges. Here's another one, maybe less obvious. How about the sum 3n cubed minus 7n divided by n cubed? Does it converge or diverge? Actually, this one diverges, and you can tell by looking at the terms on the inside and taking the limit as n goes to infinity. So I'm going to check the lim of an, right? That's what I'm doing here. And if that limit is not 0, then the series definitely diverges. What is the limit right there? Well, this you could use L'Hopital's rule, or you could just divide everything through by n cubed, which is similar to some stuff you did on the homework, I think. Dividing everything by n cubed gives me 3 minus 7 over n squared divided by 1, right? And then I can take the limit. The 7 over n squared part will go to 0, and I will remain, what remains is just 3. Of course, 3 is not 0, and so this limit is not 0. So the lim of an is not 0, and so that means the series of an diverges. So this is one way in which you can demonstrate that a series diverges. All right. Oh, here's another one. This is a much stranger one, which you cannot use L'Hopital's rule for. How about the series of sine of n? This is very weird. Even to compute this like using a calculator, it's not easy at all. This looks like sine of 1 radian, which is just some random number, plus sine of 2 radians, plus sine of 3 radians, etc. Does it converge or diverge? I mean, this is so weird. You should not expect that it does converge, but you can demonstrate pretty easily by looking at this limit. Lim an, in this case, is the limit of sine of n. Does sine of n approach any particular value? The answer is no, it doesn't. Sine of 1, sine of 2, sine of 3, that doesn't get close to anything. It just will continually bounce back and forth between 0 and 1 forever, right? This does not exist, this limit. I write DNE for does not exist, and so that means that the sum sine of n diverges. This one, the sum of sine of n doesn't really go to infinity, it just kind of doesn't approach anything. All right. Great. Let's move it along. We have just a little bit more to go in this section, and then we'll move on to the next, probably next time we'll go on to the next section. But last thing from this section is a set of unsurprising and mostly uninspiring rules for series, but we got to talk about it at least once. Rules for series. These are very similar to the rules for limits about if the limits of two things exist and it's like two things added together, then you can split the limit up into those two things added together. Or something multiplied by a constant, you can factor the constant out of the limit. We had a bunch of rules like that. We have the same kinds of rules for series. For example, I'm just going to write them down. If you have, sorry, I got to say before saying the rules, this is important. If the sum an and the sum bn converge, then you can do various tricks with them, add them together, that kind of stuff. So the first one that I'm going to say is just multiplying by a constant. If you have a constant multiple of a series, a constant on the inside, you can factor that constant out to the outside of the series. All right. This is kind of like the distributive property for multiplication over addition, because these sums represent addition. The series represent addition, although they are some kind of a weird kind of addition where you're adding together infinitely many things. But the rule says it is still valid, it is still legal to factor a c out of the, or a constant out of the series. Here's another one. If I have the sum of two things added together, we can break this into the sum of the one thing plus the sum of the other thing. If we already know that the two things on the right converge, then it is legal to break up the sum of two things into the sum of the first thing plus the sum of the second thing. And then also this rule is true for subtraction. Not a surprise. All right. Now, for ordinary limits, so why are these true? It's because the series is a limit of something, and these same properties are true of all limits, and so you sort of get these properties for free because these series are defined in terms of limits of things. These are all of them, though. You may remember, for limits, we also have properties about multiplication and division, but let me just say, no multiplication property, and certainly no quotient property. For example, what you would want to say, this is not true, so maybe I'll write it in red. You would want to say something like this. The sum of a product like that is the sum of an times the sum of bn, right? That's what you would like to say. Why don't you get a property like that? The reason is because actually this property is not even true of sums of finitely many things. Like these, of course, when I write the sums in this context, I'm talking about an infinite sum. But this property is just straight up false, even for ordinary sums. For example, if I was looking at, this is false, even for normal finitely many sums. Like, for example, if the left side, if I had just, say, two things, sum n equals 1 to 2 of an, right? That's just a1 plus a2, right? And let's say I also had the same thing for b's. Actually, it's not even true in that case. If you just have two things, the sum of an, bn, this would look like a1, b1 plus a2, b2, right? What would the other side look like? This is the sum an times the sum bn. This would look like a1 plus b1 times a2 plus b2. Sorry, I got this messed up. a1 plus a2 plus, times b1 plus b2, right? And are these the same, these two things? They are not the same. They're not equal, right? Like, in order to do the second one, you have to do the FOIL, right? And you get a different answer from this one. So the moral of the story is, in no way, you shouldn't expect any formula like this to be true in the first place, right? Not even for ordinary sums. So it's definitely not true for series. For infinite series, you cannot do that formula. Let me just say these are different. They're not the same. So you definitely should not expect them to be the same in a series. There is no multiplication property for series like that. I say there is actually some kind of extremely complicated formula for multiplying series together. So I'm not saying it's totally hopeless. If you really had to do that in your real life for some reason, there are ways to handle it, but not simple like that, and we're not going to talk about it. Anyway, a very simple application of these rules. So we can do things like, something like What if I want the sum of 5 over 3 to the n minus 3 to the n over 2 to the 2n? Can you evaluate this series? Well, you could try to like add these things together inside with a common denominator to try and write it as one thing, but that's too complicated. That would probably work actually, but I don't want to go there. We can simply split the thing up. 5 over 3 to the n minus the series 3 to the n over 2 times 2 to the n. And then compute each of those two series. These are each geometric series now. And so this one I can say is 5 over 3 plus 5 over 3 squared. Just like we did at the beginning of class, right? Here the a is 5/3. And the r is 5 over 3 squared divided by 5 over 3. That ends up being 1/3. And so this part is going to be a over 1 minus r. It's 5/3 over 1 minus 1/3, which is 5/3 over 2/3, which is 5/2. All right, so that's the value of the first part. And then we can separately compute the value of the second part. This one looks like 3 over 2 squared plus 3 squared over 2 to the 4 plus, etc. And then this we can also compute as a geometric series. The a will be 3 over 9, 3 over 2 squared, and the r will be, sorry, I wrote 2 right here. This 2 should be a 3. Sorry about that. 3 squared. I think maybe I said it right. I wrote it wrong. Anyway, the r, when I divide, it's 3 squared. All right. 3 squared over 2 to the 4 divided by 3 over 2 to the 2. What is that? When I cancel everything, I think I'm going to get 3 over 2 squared, 3/4. If you properly divide the fractions there. This is in absolute value less than 1, and so it does converge. And I get this, for this one, a over 1 minus r is 3/9 over 1 minus 3/4, which is 3/9 over, is it really 3/9? No, it's 3/4. Sorry. I'm mixing my 3's and 2's here. 3 divided by 2 squared is 3 over 9. Sorry about that. Sorry to the folks at home. And the guy who just walked by. Somebody just walked by in the hallway. It always makes me wonder, did he see that I messed up the 9ths and the 4ths? Probably not. Okay, 3/4. 3/4 divided by 1 minus 3/4 is 1/4. This one adds up to 3, I guess. Right? I hope I did that right. Yes, minus 3. Right. Yeah, so my final answer for this series, remember the point of doing each one separately was I'm subtracting them. So I'll just write it all again. So the original series, 5 over 3 to the n minus 3 to the n over 2 to the 2n, it equals 5/2 minus 3. That's it. All right. The moral is you can break up a series which has a sum or addition and subtraction on the inside. You can split it into 2 separate series. And if those 2 separate ones converge, then the original one also converges. All right. Excellent. We got 5 minutes. I think I can say a few words about the next section. So the next section, actually the next few sections, is about what we call convergence tests for series. Convergence test for series. That is, if I show you a series, can you tell me if it converges or not? Now, for a geometric, this is easy. But let me just say, in generally, it's hard to know hard to decide if a series converges or not. All right? It's even harder if you want to know what the answer is, but even like a more fundamental question or a more preliminary question, not tell me what the answer is, but just does it converge at all? Even that question is hard to answer. So what we know so far, we know that this, the geometric series, a times r to the n minus 1, this converges if and only if absolute value r is less than 1, all right? The only other example we know is this diverges. That's the harmonic series, which we talked about today. But what if I gave you another series that doesn't look like either of those formats? Can you tell me if it converges or not? That is not an easy question to answer. For example, what about the sum of 1 over n squared instead of n? Well, n squared, right? This is 1 plus 1/4 plus 1/9 plus 1/16. On the bottom, I'm writing the squares every time, all right? Does that one converge or not? Well, you can see the terms individually, they do get smaller and smaller, but that doesn't mean that it converges. Does it converge or not? Actually, this series has been studied for a long time. It comes up in some real-world scenarios. We can, in modern times, we can try to just calculate the values like on a calculator. So we could try to compute the values of Sn with a calculator. Like S1 is 1, S2 is 1 plus a fourth, S3 is 1 plus a fourth plus a ninth, and you know, I'm not going to do those by hand, but you could use a computer or something. You could compute 1,000,000 of these if you wanted to, very easily using a computer. And let me tell you, if you do that, they seem to converge to 1.64 something something something. All right. Now, when you just start typing these things into a computer and they seem to converge, that doesn't constitute a proof that they do converge because you're not actually able to check infinitely many values on the computer. Your computer, no matter how fast it is or whatever, it can only check finally many of these things. Back in the old days, this was even worse because they couldn't even really use computers to do this. They could try this by hand for a few things, but it would be much harder for them to get a good feel for whether the thing converges or not. So for this reason, there were many what they call convergence tests, which were designed to help you tell if a series converges or not. This one in particular is very weird. This was... So this specific example, 1 over n squared, this was, it was proved that this does converge, and it was actually, like, the answer was computed by very famous mathematician named Euler. Euler's number? Yeah, is E, like the number E is called E because it's, it's sometimes called Euler's number, although Euler, I believe, Euler himself called it E. I'm not sure of the history of that. I think that it is common for people nowadays to say that it's called E because E is for Euler, but actually Euler himself called it E, and I don't think his intention was to name it after himself, because that's like uncool. You don't do that in mathematics. You don't name things after yourself. Anyway, this was computed in Euler. This is like in the 1730s. Very impressive calculation without using any, computing machinery. But anyway, the techniques that Euler used were very, very strange, and you will see why, or you won't see why, but it must be very strange because the answer is pi squared over 6, which is a truly ridiculous answer in my opinion. That those numbers should add up to anything involving pi at all is crazy. And pi squared is especially weird, because usually pi comes in terms of like multiples of pi. This is a multiple pi squared. Very weird. But anyway, this is just to inspire us. What we're going to talk about next is a bunch of different ways that you can tell if things converge or not. It's not simple at all to tell if things converge. That's what we're going to talk about.